Hello, my name is Dave Robbins, and I'm giving a talk called Getting Naughty on the CAN bus with the Car Hacking Village Badge. So, welcome to Las Vegas, the home of the $30 cocktail these days. It's kind of strange. The badge here, I'll talk more about what that is, but this is the badge. And go to the next slide. What are we going to talk about? I'm just going to briefly talk about me, and I'm going to talk about the company that I run. I'm the CEO, and I'm going to talk a little bit about the badge. So just give you the basics. So if you don't really want a lot of detail, you can just skip out after that. We're going to talk about the Pi Pico, which is the CPU or the computer board that's used in the badge. We're going to talk briefly about the CAN bus, which is the technology used for networking in many industrial machines, including vehicles. We're going to talk about how we could generate and receive CAN data, and then we're going to talk about a couple methods that we can do. Some of them that you really wasn't easy to do before this new part. I'll show you the software that comes with the badge. There's actually a serial console, and then I'll talk about other software for the badge, and then hopefully some conclusions are related to that. I've been doing this kind of stuff for over 30 years. It's kind of my passion, computers, electronics. I originally was a hardware person, but there's just so much software with microcontrollers. You had to learn that, and I did every kind of software, starting out with assembly code back in the day, C code, Python. I did GPU programming, which is really interesting. I did FPGA programming, embedded software, Linux programming, etc. So, and we do all that at our work. I started Intrepid Control Systems in my college dorm room in Ann Arbor, Michigan in 1994, and we've been just supporting the vehicle electronics industry in the Detroit area and then eventually globally. And then I'm a dog person, but I'm too busy to have a dog, so I'm a part-time dog watcher. So now I'll talk about Intrepid Control Systems. We're a company, we were founded almost 30 years ago. We provide test tools for automotive. We're around the CAN hacking a lot, related to CAN, but we do way more than CAN. Automotive Ethernet is getting bigger than CAN now for future vehicles. Intrepid is a global company, around 200 people, offices in Asia, 3 in China, Japan, Korea, India, and then Europe. We have Germany and Karlsruhe, and then in UK. We are a partner for the OEMs, so a lot of the equipment we develop is basically on their specification, and we're kind of like farther. Our new products are stuff that will appear in production like 3 to 5 years out. So some of our new products like Ethernet and things like that, in Car Hacking Village, 2026, that technology, we'll be working on that. Almost looking combined with the Packet Hacking Village, because it's really a lot of the same technology. We've been working on cybersecurity tools for a long time. Foundational OEMs wanted to be able to benchmark other companies, so we developed a lot of tools for benchmarking, including just figuring out how cars work. So that we've been doing that for a long time, and that happens to have a use case in cybersecurity, just figuring out how a system works and its flaws. The aftermarket is a similar type of industry where people want to install a new radio and take out the factory radio, and the CAN bus is involved, so they have to figure out how to make all that work. You might have heard some of our main products. Vehicle Spy is common in the industry. Value CAN is our low-cost CAN FD, and then NeoVi interfaces, which we continue to evolve. So the latest one, the NeoVi Fire 3, has 16 CAN FD channels and 2 gigabit Ethernets. So Intrepid is way more than CAN bus. We do every protocol in the vehicle. CAN bus is the most fun though, because it's not too hard to learn, and you can get a lot done, a lot of hacking done with it. Okay, I'm going to give a demonstration of the badge right now. So I'm going to switch to the full screen mode. Okay, so what we have here is the most interesting part here is this is the Pi Pico right here, and this is the CPU and the USB interface for the badge. The Pi Pico has GPIO around it, and we're using some of the GPIO, and we actually connect it to a CAN physical layer here. This CAN physical layer is from Microchip. It's capable of CAN FD as well, although we're not doing any CAN FD with the badge. That's basically something that, based on the talk, you could do CAN FD based on what I talk about. There's two buttons, and then there's two switches. One of the switch turns on and off the power for the battery. The battery is just used to kind of flash an LED while it's not plugged into USB, but most of the badge features only run on USB. So basically we have some just regular LEDs that are just powered off USB, and then these are actually controlled by the CPU. One of the switches doesn't do anything. There's two buttons, and you can hear that there's a buzzer on the back. The badge itself has a silkscreen that kind of explains a lot, and then there's a QR code that links to our website has more information. Just a heads up, some of the silkscreen has errata in terms of what pin's connected to what. So for example, the buzzer, it says GP19, it's actually GP20. So if you do sit down and write some software for it, Python or C++ or BASIC or whatever your poison is, go ahead and do that. What it does when you just plug it in is you can push the button and it'll start a countdown. And then what that's going to do is it's going to launch a kill on the CAN bus. So it's actually going to generate CAN messages out of this connector, which you would wire in, which I'll show a wiring setup I got later. So just to give you an example, there's if you hold one button, it does one kill. Another button, it does another kill. If you hold both, it does a third kill. And I'll explain what those kills are later. But we'll just go ahead and try one. Now you can see this LED illuminate. This is the actual CAN bus activity. So we're sending out CAN messages right now, and the idea is that we're either doing a type of denial of service, or we're sending incorrect frames. And there's actually 3 different kills, which I'll show you later. But this is never going to let you talk, so I think this is generating 0 frames, which if you generate continuous 0 frames, that's the highest priority message. It will disable the CAN bus. Now if you go plug this into your car and things go bad, don't call me, okay? Because older cars weren't necessarily tested to be like attacked. So use at your own risk, or rent a car, I don't even know. But the first time I plugged into like an old Ford, not with this badge, but I just had the CAN bus speed wrong, and the whole car just shut down, and I had to just disconnect the battery and reset the whole car. So you know, your mileage will vary. I'm interested to see what people in the community plug this thing into. So that's the basics of the badge. I'll demonstrate the USB software later. So this right here are some screenshots of the USB console. So if you plug this in to Linux or Mac or whatever, and you open up a serial console to TTY, S whatever USB the serial port it is, this will show up, and it will allow you to configure the badge. The kills with the buttons are predefined kills, and then the menus allow you to configure out exactly what you want to do. First, let's talk about the Pi Pico. What is the Raspberry Pi Pico? Traditionally, the Raspberry Pi Foundation has been building single board computers that are based on Linux, and then the Raspberry Pi Pico is the first single board computer that is just a microcontroller. So the microcontroller runs almost no OS or little or no OS. It's lower cost, lower power. It's a lot different than the Raspberry Pi. Now you might hear something called RP2040. To clear the confusion, is the Raspberry Pi Pico is the name for the single board computer. The microprocessor or the microcontroller on the board is the RP2040. Now, with the Raspberry Pi, they didn't sell the processor independently. It's just you buy the board, and then you can't buy the chip and make your own board. but that's different with the Raspberry Pi Pico. Now, the Pico board costs between $4 and $6, and they just released the $6 version I think last month, and it includes Wi-Fi. So you can do Wi-Fi type projects with this that connect to an access point or act like an access point. So it's pretty cool for $6 how much you get. The board itself is programmed and it's supported by Raspberry Pi in C and C++ and Python. So there's I believe a MicroPython. There's MicroPython port for Raspberry Pi or Pico, which you can write, quickly write scripts. The board, it has the Raspberry Pi community behind it, so I think that's what's most interesting to me, is that getting support and finding other people that did things. The initial release was last year, and I think maybe it didn't get as much attention as it should have because it didn't have wireless. So now that it has wireless, it'll be really interesting to see how this board does take off. The tools are all free. So like if you've been in the embedded systems area for a long time, its tools are a pain to get or very expensive. I mean, at work we've paid, $10,000 for a C compiler because, for the PowerPC, because that was all that was available at the time. But these tools are all free: GCC, Visual Studio Code, and then even a hardware debugger. You can use a Pi Pico to debug another Pi Pico. So you can use the $4 Pi Pico to debug the other one, which you got to have a debugger if you're doing any serious work. But the most interesting feature of this board, and the only reason I learned about it, is because it's available. Availability of any type of microprocessor chips right now is so important, and right now, at least right now, you can get these in thousands of quantities for projects. So like for the badge, we bought reels of these months and months ago, so we made sure that we had all the parts we needed. The badge hosts the RP1210 microcontroller, which is when it first came out, I looked at it and I just dismissed it as another Me Too product. But since it was hard for us to source, all last year all we did was redesign our products at work for availability of components, which was not the most interesting work, but we learned a lot. So this year I took a look at what was available, and this part is super available, and it's 70 cents if you buy the full reel, and you can buy it directly from Raspberry Pi. So I took a look at it, and I was pretty impressed with what it had. First of all, a Cortex M0, who cares? But there's a new trend to have like microcontrollers that have multi-cores, and it opens up some interesting applications, including the one that I'm talking about today. But the most, I think, breakthrough thing that this part has is it has 8-bit bang processors called a PIO. And I feel like there's so many problems in my career in embedded that are solved with this. It's just a total breakthrough, and it's a game changer, especially on such a part that's so low cost and low power, which before your really only option was FPGA, which is very complicated tools, very power hungry, very expensive. So it's a game changer for the industry. Another thing is it's very fast, 125 megahertz, and that's a clock rate of 8 nanoseconds. So you can do a lot, and things like bit banging CAN bus at 500 kilohertz is well, I'm not going to give it away, but it could be possible. There are videos online where people have overclocked it to over 300 megahertz, so feel free to check those out, and then use at your own experience. So if you overclock it and you test it and everything works, that's great. So if you want to bit bang things at 300 megahertz would be like 3 or 4 nanoseconds, or under 4 nanoseconds, go ahead and do that. It has USB, which is really useful for bootloading and connecting to a PC. It's 12 megabit, which is disappointing because the thing is that the PIO engine can move so much data, it just doesn't have anywhere to go. It can't go up to a PC. but it's a 70-cent part, so that's that. It's really great at PWM channels. Using the PIO and the PWM, you can generate a PWM on every pin of this device. So like things like robotics applications where you're controlling servos, or you have a bunch of LEDs that you want to dim, and full color LEDs. It's really awesome, and it's got like the standard digital peripherals, and the pin mapping is real flexible, so it's really useful when you're designing boards. It does not have onboard flash, so it actually has to load code from a serial flash at boot up, which is not so great if you're used to microcontroller. And there's no code protection, so like if you design something with this, it will be very easy to copy. And voila, this part is on the DEF CON 30 badge. So this part right here is RP2040. So I'm not really sure why they chose it. I'm really interested to learn, but I would guess having it available is probably maybe a good reason. And I'm really excited to learn more about this badge this week. And of course, on the back of the badge is the Raspberry Pi Pico, and it's just soldered down. And we actually place this with our machines, our SMT machines. So it came on a reel, it's placed right on the board. And our guys did a really good job where the pins, if you look at the hole pins, they are totally open. So you can put a pin header through the DEF CON badge, and you can use the rest of the I/O. So think outside the badge, use write some code, use the other pins to do stuff, and have fun. All right, so now I'm going to talk a little bit about CAN bus. It's very popular, and it's kind of a huge focus of the car hacking village. The CAN bus is also used in many other protocols. So like a boat, if you have a boat, there's something called NEMA, I think 2000, and that uses the CAN bus. So we were talking about like all the different ways we can make different badges. Like we could have boat kill. They use it on airplanes. You could have airplane kill, which no one liked that. No one liked that name because we don't want to get picked up by the NSA at DEF CON. But anyway, the CAN bus is used everywhere, and all these attacks would work on that. What is the basics? When was CAN bus created? Who cares? I mean, really, who cares? It's been around forever. It's going to be around forever more too. So everyone listening to this, when you're on your deathbed, you're going to look over at that machine keeping you alive, and it's probably running CAN bus. So, and it's just a great, inexpensive, cheap protocol, and it's very robust. And of course, when people say, "What does that mean?" It's like you can really configure it all around, and it still probably will work. And which is a terrible way to design a system. Ideally, you design the system correctly, and then whatever happens in the field, it still works. But I've seen systems over the years where they just take that robustness and use it as a feature. Why did they make the CAN bus? Who cares? Go find another video online to learn about why they created it. But we're going to talk about the what and the how. And this is just a basic CAN network where we have two wires, CAN high and CAN low. I like to think that we invented the colors for CAN high and CAN low, but I just remembered at the beginning, we always said yellow is like the sun and green is like the grass, but it's been so long, I don't remember. But each end of the network is terminated. So CAN needs a termination because it only drives the CAN bus in one direction, and then it relies on the network capacitance to pull it back down. So without that, your bits will be all messed up. And we actually have a feature in our product where we generate a pulse on CAN, and based on the fall time of the transceiver back to recessive, you can automatically determine if the network is terminated. What does the bus actually look like? So if you connected an oscilloscope to the bus, there are two signals, CAN high and CAN low. And CAN high, whenever there's a dominant bit, it goes high, and CAN low goes low. So it's a differential bus, so the receiver actually measures the difference between the two lines. And the difference is real important because in a vehicle, the ground is used to carry current for all the different parts of the chassis. So what happens is whenever currents are flowing through the ground, there'll be an IR drop, which will change the voltage at the ECU. And if it goes, if you're using the ground as a reference, you can have some real interesting problems, like when only certain motors go off, you lose communication. So having a differential network is a huge benefit. Now, how do we get to this protocol? Well, on the badge, the phi on the badge, this little part, that can cost between 30 cents and well, last year people were selling them for $8. But that part for microchip, it takes in a digital logic signal, and then it generates the actual physical layer system. So with the pi pico, we'll be generating this digital signal, and the phi will generate that. What's important when you configure the network? Now, when you first look at CAN and they show you this diagram, it's just like you immediately have you need aspirin or ibuprofen immediately, because it just gives you a headache. And who cares about time quantum, whatever. The main important thing about this is the bit time, and that's the length of the actual bit, and then the sample point. Those are the two things that care. So if you got those correct, the CAN bus will work. Now the sample point is when the digital logic actually looks at the bit to determine if it's 1 or 0. Okay? So what happens is you can have it wrong, but then on certain networks, if you wire it a certain way, you'll get errors. And there's actually an attack by Canis Labs that you can do with the badge called the Janus Attack, which messes with this, which I'll have more information about that later. So what do we want to do with the badge? We want to generate CAN bus frames. So now I'm going to talk about how we're going to do that. What's really awesome, and I probably didn't realize this at the start when I looked at this part, and having 2 CPU cores in an embedded system is really useful, because normally bit banging is just not possible, because you have a core and it's got to handle USB, or it has to process some data or something like that, and you can kind of do some stuff with interrupts, but it's never really deterministic, and you can stop everything in bit bang, and that does work, and we've did some stuff with that. But if you have to bit bang for too long, it kind of things stop working. So for example, like USB on this badge, it's interrupt driven, so if you don't service it, it will actually disconnect from USB. So it's kind of annoying when you're using a debugger. But having a separate CPU core allows you to do these bit banging, and it'll still have your full application running. So you'll notice when I sent the CAN messages with the badge, it sent the CAN messages, and the LEDs flash, and everything else still works. So it's pretty cool. Now you can have a second core, but how does it use? How do they work together? And with the RP2040, they did a really good job of allowing it to operate independently if you use it correctly. So there's essential for bit banging is you want to be able to be deterministic. That means when you write the software, it's exactly going to have that many cycles and that timing and everything. And they did so the way you do it on this part is they have a feature called single cycle I/O, which I'll explain. There's something called a bus matrix with SRAM, and then they have FIFOs between the cores so they can communicate. So I'll talk a little bit about that. And all these diagrams are from the RP2040 datasheet, so you can learn more. It's really fun. Now there's other CPUs that have dual cores out there. So NXP has them, Microchip has them. I would say I can't tell you if they're done deterministically, although Microchip does have a DS-PIC core, which I used to program in, and I love, but it's only 16-bit. They have a dual core now that runs at 10 nanoseconds. Here we go, single cycle I/O. So normally with an ARM processor, what happens is they have load and store instructions, meaning that's the only way memory is changed. It's through these instructions, which require access to the bus, and they're always multi-cycle. So to do a load, it will have to go on the bus, and then the I/O itself is memory mapped, so it will be a specific address they have to go to change. Now, with the Cortex M0 Plus, they have this feature called single cycle I/O. So the logic in the core actually looks at what address that you're writing to, and if it happens to be a specific address, it can change that logic with one cycle. So the load and store instructions for those addresses take part 8 nanoseconds. So you can actually there's a register that will allow you to toggle a GPIO, and you could just have inline code that you could generate clock pulse every 8 nanoseconds. So you can bit pang things, up to 62 megahertz, 62 and a half or half the clock rate. So it's a really cool feature for bit banging. Now, do you really need this to do CAN? Because like if you look at the 8 nanoseconds compared to like a standard CAN bit time at 500 kilobits, which is 2 microseconds, do you need single cycle I/O for that? I don't think so. But like if you want to do a faster protocol, like maybe CAN-FD, then you want to have you want to be able to save every instruction. Now, this is the other part. So the CPU just exists in the part, and it needs access to RAM, and it needs access to I/O. So the single cycle I/O takes care of the I/O. Now the other part is you need RAM, and you need RAM for your stack, you need RAM for your code, because this is a processor that there's no flash or anything. And so when you go to access the RAM, if you have to share the RAM with another core, that's a problem, because depending on priorities, who gets it and cycles. So the trick is they created this thing called the bus matrix, which is actually kind of hard to see right here, but it's basically a logic device that there's certain masters, which in this case there's 3. There's the core 1 or core 0, which is the first core. It gets kind of confusing, and then there's second core 1, and then DMA, and they all they go into this little box called the matrix, and then there's all these things that hang off of it. And the beauty of the matrix is, as long as you're not accessing the same peripheral at the same time, or the I don't know what the best, let's just call it peripheral, that there will be no waits for that resource. So for example, if core 0 is talking to this SRAM, and then core 1 is talking to another SRAM, there won't be any blocking. So that allows the core to run. It allows the core to run without any blocking, so it gives you a deterministic clock rate for the core. Now, it's important to know, if you use this part, depending on what address you access these SRAMs, they're striped. So if you might take one address, but the next address will be on this SRAM, and it's actually a cool thing, because it allows, if you're running code out of the SRAM from both parts, they'll not always block each other, so that's interesting. But like if you're going for determinism, you can't use that striped feature. So in the code that I wrote uses one of the 4K SRAMs. So all the code and the stack all go in there. Okay, so this is basically a summary of what I just said. We use this independent SRAM. They call it ScratchX actually in the code, and then the second core. Another thing I wanted to mention that I might have skipped is on this first part here, there's actually a FIFO, and this allows you to communicate between the cores, and that's also deterministic. So core 1, there's a FIFO that goes in one direction, and then core 0 has the opposite. So core 0 can write to the FIFO and not block, and then core 1 can read that FIFO. You can check if something's there and use it or not. And that's how we actually trigger the CAN transmission. So I'm going to stop and I'm going to do a code demo of the CPU bit bank. So this is going to be Visual Studio itself. So I'm going to let it stop. I'm back and I'm going to show the code for generating the CAN message. This is Visual Studio 22, and I have a plugin called Visual GDB, which has some tools for using Visual Studio 22. Actually, all the previous versions for embedded processors. It's pretty good. I'm having some issues with the debugger between the two parts, but let's go ahead and look at this. So this particular file is called CAN Message Builder, and this is I'll show you the first step. So basically, what happens is there's an init function here, and it looks at what the type of kill it is. So this is an arbitrary kill, and then it will load some settings in the kill, and there's a function called create CAN message bits. So we're going to go look at that. So there's this object called obcan, which is it takes the CAN message and creates ones and zeros based on the information. So we're loading in the CAN ID, the different pieces of the extended frame, the data, and then calls this function called CAN to bits. So what it does is it goes through here and it checks the bits and then adds them to an array. And I tried to do CANFD, but it's not supported. But it just goes through the different fields of the CAN protocol and generates the bits. And if we go look at this function, it's kind of interesting. It actually does the CRC and the bit stuffing of CAN, which I'm not going to explain in this video, but that's a key parts of the CAN protocol. So that generates the actual ones and zeros, and then if we come back to where we started, there's this build CAN message, and what we have here is there's this class called ARM. So normally you would use an assembler, which is a separate source file, but I've written a C++ class that dynamically generates the Cortex M0 instructions. Now there's only like 30 instructions in the Cortex M0, which is why I thought it wouldn't be hard to just dynamically generate messages, and it wasn't too bad. The instructions have derivatives, so I only really implemented the ones I'm using, so it'll probably grow over time. What's really cool about the Cortex M0 is the instructions are binary compatible with all the Cortex M. So M stands for microcontroller. So some of the more popular ones are Cortex M3 or 4 that have like more advanced instructions and floating point, and M7 as well. They're out there. So this code technically will work on those processors. Of course, the delays are different because they're designed differently. So some of them have like dedicated RAM, or they have a different number of stages in pipelines, so things take longer. Anyway, what we're doing, the first thing we're doing is we're initializing the program at the address of that particular SRAM. Now the key part about a Cortex M part is the addresses that you call have to have a 1 in them. Otherwise you get a hard fault, because 1 is the first bit says it's a thumb or ARM instruction, and the Cortex M only supports thumb. So that's a weird thing I had to learn. Lots of crashing and hard to debug. One of the problems I have with my setup right now is that the second core is really difficult to debug. So there's the tools that I have and I looked for. I haven't seen any really great solution to debug both cores, which is kind of a bummer. So anyway, we're basically generating ARM assembly here. Move, immediate, logical shift, rush here, and then there's literals. This is kind of interesting. ARM is a 16-bit instruction set, so it can only load small constants. So the way they do it is they actually just, in the code itself, they'll have the 32-bit constant, and then they'll load that from memory. So the assembler actually already does that, but like we do it dynamically. So going through the code here, here's where we actually generate the code for generating CAN. So we have the CAN, we have the bit buffer, which is just ones and zeros at this point, and we either generate a set instruction or a clear instruction. So what the clear instruction, it's just storing data to the memory location where it controls the output. So there's a different address for clear versus set. And then it does a branch and link, which is basically calling a subroutine to a delay. So based on your bit time, the delay will be different. And I'll show you basically that. And at the end here, we actually build a delay function. And depending on what you're doing, you're generating, you're gonna build a delay for your bit period, and then you'll build a delay for a consecutive message, and that's called the interframe period. So we'll go to this. So here, you pass in the number of the delay in nanoseconds, and then it generates a cycle accurate delay in assembler. Now, how did I get this perfect? I used an oscilloscope and I verified it. So step one, I calculate it. Step two, it didn't make sense. Step three, you go back and trying to figure out what went wrong, and eventually that the instructions or the knowledge matched the actual the code. So what's cool is the difference between Cortex M0 Plus and all the other Cortex M's. It has a two-staged pipeline, so that means that the branches take 2 cycles versus 3 on all the other Cortex M's. So if you want to port this code, that would be definitely a consideration. But the end result is the main core software calls a function called sorry, that's the wrong source code. Start, and then we'll call this thing called send message. And all this does is if the FIFO is ready, it pushes a value into the FIFO. And then the second core this is process core 1. It just basically runs the program and sends the message. And it doesn't show where it's checking the FIFO, so I actually have to go to a different source file for that. So here's the actual source for the main. It's checking the FIFO, and then if it does, it calls that function that will trigger the send. So this is the actual initialization for the code. And this is where you start the core. So the first core starts the second core, and that generates CAN messages. Okay, so now you might not understand on that code, but the main purpose of the presentation is to kind of give you clues and give you the idea in your head that it's definitely possible to bit bang digital protocols that in the past I think were too fast to do that. So for example, a CAN frame is typically the 500 kilobits. The bit time is 200 or 2000 nanoseconds. So with an 8 nanosecond clock rate, you have 250 instructions between each bit that the CPU can use to deal with CAN. So it just opens up some really cool opportunities for CAN hacking. Now, of course, now we want to receive CAN bus frames. So how could we do that? And this gave me a chance to talk about the BitBang processor. So the BitBang processor is a revolutionary. It's a huge part, it's a huge piece of this part. So it's such an important part. It's got its own section in the data sheet. It takes up a huge part of the die area, but it's really just super capable. And what it is there's actually 2 of them, and the 2 PIO modules each have 4 BitBang processors. And the 4-bit bank processors share some resources and then have their own independent resources as well. It's what's kind of cool that you can, there's ways that the bit bank processors can kind of start at the same time, and since they're all cycle accurate, you can do a lot of really cool coordination between the two. But it's very complicated. It's not complicated. It's actually very simple. But how to use it for a particular application. You just have to sit down and look at the instructions and see how it works. But I did this just a very simple, crappy can receive. So what does it have? It has 8 different instructions. Doesn't sound like a lot, but low number of instructions are good because it maybe allows you to do an understanding of it. It's got FIFOs to communicate with the CPU. So basically the CPU will throw data in the FIFO and read data out. So for example, if you were doing CAN transmission, you would put those bits from CAN into that FIFO, and then the bit bank processor would read them out and send them. For this example with the receive, I sample the bus and then I slide the bits into the FIFO for the CPU to read. There's 32 instructions only, and they're shared within the PIO by all the PIOs. So the CAN receive core I'm going to show, or the code, it takes like say 10 instructions or something. All those state machines could run simultaneously with those instructions. So if you wanted to capture 8 CAN channels at the same time, you can do that because it all works in parallel. Pretty amazing. What are the instructions? Jump. The jump, it's a conditional jump or non-conditional jump, and it can jump anywhere in those 32 instructions. It can jump on IO pin, it can jump on, there's some scratch registers or accumulators, stuff like that. Wait is waiting for usually a pin to change state. So for CAN, we're waiting for that start of frame. So as soon as that goes low, then it signals the start of a new CAN frame. In and out are just like USB, where they're the direction to the host. So in means it's going to the CPU, and out means it's coming from the CPU. So in is basically shifting data into a shift register, and then out is out, or from pins into a shift register, and then out is out from a shift register to pins. So if you're doing CAN transmission, use out. CAN reception, we use in. Push moves data from one of the registers, either the shift register or the scratch register, into the FIFO, and then pulls a data value out. Move just moves data between the different parts, different registers in the part. And the IRQ generates interrupt for the processor, which we actually use for the CAN reception. And then set will actually set IO pins or set values of the scratch registers. Okay, so now we're going to do a demonstration of the receive code for CAN bus. Okay, so we're back to the Visual Studio, and this is in a class called CAN RX. So just like there was a class that was created for generating Cortex M0 instructions, there's also an assembler that you can write assembly code for the PIO. But I wrote a class that just generates the PIO. It's very simple, and I want to dynamically change them in code. And honestly, the assembler, it just is, it's easier to use code. The only downside is that you have to have this code in your project. So the assembler that I wrote is extra code in your project, where the assembler, if you just use theirs, it just works just like a C compiler, which is, it's actually really cool how they did that. So when you learn more about it, but we're just going to go through this code. The CAN receive and the badge is kind of not a very good one. It didn't have a lot of time to work on it, but I just want to demonstrate the PIO engine. So it only works at one specific bit rate, which is 500 kilobits. So the first thing you're going to do is set up the clock period of the PIO. Now it can run at 8 nanoseconds, but there's advantages if you can use a closer clock rate, which I'll explain. So this actually sets it up so you have 32 different clocks per bit. Okay. So the first thing we do, we initialize the PIO engine, and then we're going to set up the FIFOs. The FIFOs are configurable, and there's a lot of cool things you can do with them. but two of the features that I use in this is there's a 4-word, so 32 bits, 432-bit word FIFO on in and out, but you can actually join them so they can be all in or all out. So I actually join those 32-bit FIFOs, which means there's 32 times 8 bits, and that's actually smaller than a can frame, any can frame. So you can actually use the FIFO to capture an entire can frame, which is pretty cool, without any CPU intervention. So we set the pins. We're only using one pin, and this is the RX pin off the can transceiver. Then we start the assembler. We start encoding. I'm not going to talk about wrap target, but we add a label. So for jumps, you need labels. So this is just like in the assembler. The first thing we're going to do is we're going to set up a interframe timeout. So this is how we detect when the can message is done, is there's a certain number of bits in between the messages. Then we're going to go ahead and sit ahead and wait for can to go low. So this false means low. So this is the wait instruction. Now each instruction can have its own delay. So if I look in there, each instruction can have its own delay. So that means after the instruction executes, it will actually wait this amount of time to go to the next instruction. So that's where the time determinism of the state machine is extremely useful. So what we're doing here is we're just waiting for the sample point to be 75%. And then what that is since I set up 32 clocks, it's 24 clocks to the sample point. So here we're just going to fall into this, and then we do a jump, and we do a jump based on the can RX to determine if it's high or low. Now what's weird about the jump instruction, it only will jump on a high, so you have to design your code. If you wanted to do something when it's low, then you gotta just jump somewhere else. But it totally works. It just uses another instruction. That's all. So if it doesn't jump, can is low. When can is low, we refresh the timeout, and we're storing this into this Y scratch register, and then we call the in instruction to sample the can line and that puts it into the shift register. And then we just jump always back to checking the can line. Now, why am I checking the can line immediately? I'm actually not, because in this in instruction we're waiting 32 clocks. So 30 clocks is one whole bit, and then I subtract away 4 because there's actually each instruction takes 1 clock. So basically I took away the clocks of the instruction and then resampled the bit. If can is high, which is the idle bus, we sample the bit and then we jump, but in this jump we actually decrement the Y scratch register. So what this does is it will, if Y is 0, it will not jump. If not, it jumps and then decrements Y. So it's kind of a post decrement. If Y is 0 at this point, then we fall through the loop to this, and then we flush the FIFO. So the FIFO will automatically flush when it fills 32 bits, but since the can is not going to end on a 32-bit boundary, we have to flush that data in. And then we actually generate an interrupt to the processor. Okay? And then this just goes back to the wait, which is waiting for the start of frame. So this thing is just going to run, and then anytime it sees the start of frame, it's going to sample the CAN bus till it's idle, and then it will put that data in the FIFO. Now, I call this a crappy CAN decoder because it's missing a key feature of CAN, and that's called resynchronization. So whenever there's a dominant edge, whenever the CAN is driven by the transceiver, you're supposed to check the time resynchronization. So like if you know a lot about UART time, the receiver, since it's an asynchronous protocol, it has to derive its own the sample clock from the bits. So CAN, what it does is anytime there's a high to low transition, it does what's called a resynchronization, where it compares to where it thought the edge was and then adjusts its clock. Now, I didn't do any of that. Is it possible to do? Absolutely, it's possible to do. It's just more work, and I didn't have time to do that in this example. And honestly, with the PIO, receive can totally work. The only problem with receive is acknowledgement. So like the PIO, I don't think can keep track of which bit is which and decode but maybe handshaking with the CPU can do that. But like knowing where to set the acknowledgement bit is definitely going to be the biggest challenge. Now, normally, if you're just connecting to an existing bus, you don't care about the acknowledgement, or you're just spying. So definitely PIO for receive totally could work. And transmit really is very simple. You generate the bits, and then you just compare. At the sample point, is that the bit that I sent? Um, is it the same? If it's the same, then your transmitter. If you're not, then you just stop transmitting. So that I think that would be very easy to do with PIO. So let's look at the other functions in this. So how does the CPU actually get access to that data? So every so often, the CPU in its main loop will call process, and what it does is it looks at the message data count, um, and then it just parses them and it changes the bits. It destuffs them, so can bit stuffing, and then it builds a can message. Now, where does this thing get filled up? There's actually an interrupt that's called. So we have an interrupt callback here, and then that is called here, and we actually read the FIFO into this temporary data section, which is basically then eventually processed by the main core, which is this code. This is just an example of it can be done, and we'll go back to ending this presentation, the demo. We have our picoscope up here, and I'm gonna just do some quick settings. So first of all, channel A, I have a 10x probe, and I want the range to be plus or minus 5, so we can see the voltage. And I have the probe here, and I'm going to touch the I/O pin of the CAN transceiver. All right, so it looks like we got a good waveform there. So what I'm going to do is I'm going to run one of the kills. I don't have another camera on the badge just because I ran out of USB ports. So what we're going to do is we're going to zoom in here, and this is just generating error frames. I'm going to set up the trigger, and this little diamond is the trigger point. You can move it wherever you want. So we're just put it right there. So we're basically just turning the horizontal, and I'll go ahead and stop that. And we have our cursors here. Now, this is the logic waveform, so outside of the transceiver, and we're going to go ahead and measure this, and you can see we're at almost exactly 16 microseconds. So a 2 microsecond bit time that's going to be eight pulses. Okay, so that's what we're generating that's the your cans in jeopardy kill. And then kill with zeros. Let's go ahead and do that. You can do it from the USB prompt, or it's just more fun to do it with the badge. All right, so go ahead and run that, and I'll turn the trigger back on, and yes. So can message. So you can see it's generating. So this is the idle bus, and then this is basically CAN ID 0. The picoscope has some CAN decoding features on it. That's really cool, but I don't have time to show that right now. And then finally the random kill, which is not as much, not as exciting. Hold both buttons for the random kill. Now this one generates random delays between the messages as well. Oh, wait. Just random size message, random CAN ID. It will actually generate errors once in a while as well. All right. Okay, so that's the predefined kills, and let's go ahead and I'll talk about the software. First of all, there's a version number. I think we're releasing 5 or 6. 6 has the power management features to run off the battery. So that might be the one you get. Uh, it shows how many message bits you're generating, and it tells you the time. So this, you know, standard CAN message is like 250 microseconds, and that's this particular message right here. There's 16 stuff bits. So it's kind of a waste in CAN. It has to generate these stuff bits. So depending on the data in the message, it's either going to be shorter or longer. The bit period, so this is the actual baud rate, so 200 nanoseconds. And then transmit count is how many you're going to send when the kill is issued. And that's just for the arbitrary kill. That's this one down here. And then you can actually generate an interframe period that's nanosecond accurate as well. So if you wanted to do like 10 milliseconds between the message response, that lets you see CAN messages. Can ramp the CAN data, so that will change the data in the CAN message or interframe. Then ramp the interframe period. Uh, that's the width between the message you can ramp. You can actually ramp the bit period. So if you wanted to send, 500 kilobits and then mess with the bit timing to see how an ECU responds, you can do that. And then ramp CAN ID will change the CAN ID. So these are the different settings. So let's go ahead and change the CAN message. So this is the CAN message configuration. You can change the CAN ID, the length of the frame, the bytes. You can add invalid CRC, invalid R0, which is a common issue that with a lot of CAN controllers, it wasn't defined what to do about that. You can change the interframe separation time and the end of frame separation time. So if you want to violate that rule where you send a message earlier, you can do that. Generated error frame. This just generates that error frame that you saw in the Jeopardy kill. And also, you can have an extended CAN frame with 29-bit IDs, and that's what's used in trucking and industrial applications a lot, boats. Remote frame, this is a frame that no one really uses, but why not see what happens? So I'm going to go ahead and generate different CAN frames. So I'll hit 3 and then enter in some different bytes. You see we changed the message. Mm. And then I'll quit. And then what I'll go ahead and do is I'm going to kill the boss here with, okay, so we can see the scope. And I'm going to hold the scope probe on the CAN chip. And then I'll go ahead and okay. And then you went ahead and generated a lot of messages. So let me slow down the scope. And I'll do the kill again. And there you go. There's your message. Now, what's cool about the 555 is messages is that it's shorter. I don't know if you know it, because it has a lot less stuff bits. You don't need stuff bits if every other bit is different. Uh, so let's do something. I'll send the kill, and we'll ramp the CAN data. So I'll select 6. And then there's different patterns you can generate. Walking ones is pretty cool, where it just shifts a 1 through the CAN data every frame. So how to do that? Oop. Did you catch that? This is where the vehicle spy tool will come in handy to see actually what it's doing. Uh, Now, just to show some of the other features, I'm not going to demo uh, the uh, the CAN response refrigeration. And what this does is you can set up a CAN ID, and that will trigger the arbitrary kill. So you can transmit arbitrary kill. So when it gets 342, it will trigger the kill. There is a bug with this version where it actually kills the badge, so it's kind of like suicide feature, I guess. So the kill kills itself. But you can just power cycle the badge and it will do it. And then there's a CAN monitor. The CAN monitor is actually using the PIO code I just showed, and it only really decodes the CAN ID at this point, and there's some issues with the data. But the data is correct. It's just the decoding, transiting the bit stream into the CAN messages. There's a bug in it. Anyway, that's pretty much the badge. And if you have any questions, I'm going to be at the DEF CON Village on Friday all day. I might be there some Saturday. I'm not sure, depending on what else is going on. Okay, just wrapping up here. Uh, there's a company called Canis Labs that had came up with the idea of using the Raspberry Pi Pico with CAN, and they made a couple of products. One is just the Raspberry Pi Pico connected to a transceiver. That's called CAN Hack, and then another one it actually connects to a microchip CAN controller, so it can do CAN bus, and they have an API. But they support Python very well. The CTO of Canis Labs, Dr. Ken Tyndall, he has ported their software, and he's did a number of talks about cybersecurity online that are pretty interesting and a lot of attacks. But he designed those attacks into his PyPico code. Uh, what's awesome is that the his CAN hack board is basically identical. It's the PyPico connected to a CAN pin, so he ported his software to the badge, and it's available for download. So you can generate different attacks from a CAN or a Python REPL. So I encourage you to learn more about that port and as well as the different attacks that badge can do. So he's got some research that he's done with it. So please check that out. It's really cool and a real great bonus for the badge. And finally, conclusions. The RP2040. Take a look at it. It's super interesting. The dual core CPU and the bit bang engine at high clock rate, which you could probably overclock. You could probably do a lot of destruction to digital protocols. Everything's really a digital protocol now. So like wireless, all it is digital protocols, and they're on a carrier. And what's interesting about engineering and where cybersecurity happens is uh, people are testing things, but they don't test it to the point where they need to. It might be just impossible. It's just hard enough to get things working these days. So you ship the product, and then maybe 10 years go by, and then you come around with something like this, and then you interact with the protocol in a way no one ever thought, and you can discover some interesting 0 days and things like that. So I think this is a real interesting tool for any protocol. This is just an example on the CAN bus. So you can use that CPU cycle accurate 8 nanoseconds, or less, um, and you don't have. It's not like cumbersome like an FPGA. So you can do a lot of cool stuff. And can you do CAN bus with RP2040? Absolutely. Uh, 500 kilobit CAN bus. You have 250 instructions between bits. Now you would have to do it the exactly opposite way as I did it. So what I did, I used the CPU to do transmission because the arbitrary transmission was the main feature of the badge, and then I used the PIO to do reception. Uh, Actually, the opposite will work, where you use CPU to do reception, because then you can do things like decode the CAN bus data length, uh, generate the uh, generate the acknowledgement in the proper location, things like that, which you really need to keep track of numbers and do some math. Uh, but the PIO absolutely can do transmission, and they're totally independent processes. So you can transmit the um, with the PIO while you're receiving with the CPU, and you can do arbitration by just checking the bits. If you put it on the bus, it's not there, you stop. So it's totally possible. I don't I don't know about CanFD. There's some bit time changes and stuff like that. I would have to say, I only spent like a few days with this, and there's a lot of creative ways to use the CPU and to use PIO. So I think, someone with a lot of time and talent probably could do a lot with this. Anyway, and hopefully the conclusion is the CHV badge that Intrepid has designed is pretty awesome, and maybe I would like to think it was one of the best badges, at least in terms of functionally what it can do, and it's a great value. So I hope you pick one up. We made a ton of them in our factory in Troy, so please take a look, and I would be great to meet you in person and answer any of your questions in the village. Or contact me on Twitter or LinkedIn. And if you're super talented, Intrepid's always hiring. So that's that. I had to put the plug in. But enjoy DEF CON, enjoy Vegas, and have a good trip home.